we'll get going with further discussion. So yesterday's session was also supposed to cover the work interaction and the related matter, and that's what we will now take up first before going to the discussion on first law and then subsequently to zeroth law. So to get the ball rolling, in the lectures 4, 5, and 6, the work interaction has been expounded. Okay? And it's been introduced in a certain fashion, how you classify a certain energy interaction or a transaction between two systems separated by a boundary as work. So this is what we call thermodynamic definition of work. And prior to that, of course, several examples have been provided in the lectures, and those were used to sort of set the tone for the thermodynamic definition of work. So my question really is, and today we'll try to be a little bit time bound because we need to cover these materials. So let's be focused on what we are referring to as the topic here. So with reference to this work interaction, what I would like to ask is what is the pedagogical content that you thought you could possibly incorporate in the course that you teach. So that's really what we would like to know. And with that introduction, I'll request someone to go ahead with this.
Good morning, sir. Sir, actually, pedagogical content knowledge is a type of knowledge that is unique to teachers and is based on the manner in which teachers relate their pedagogical knowledge, actually what they know about teaching. So as a subject point of view, thermodynamics is the basic subjects, and like physics, chemistry, math, it is also a very important subject. But when the student come in second year, because in our university, the curriculum in second year curriculum, the basic subject is thermodynamics. So when I teach thermodynamics, I feel that there is a there is a lot of troubles to connect the students with the practical things. So I just want to tell them, connect yourself with the thermodynamics. Like if you are solving any problem of thermodynamics.
I'm sorry to interrupt, but what specific question has been posed is that this energy interaction called the work has been defined in a thermodynamic sense in the lectures, initially in the lectures 4 through 6. The question was, with reference to that description and the way the thermodynamic work has been explained, or work from a thermodynamic point of view has been explained, how do you think you can incorporate that in your teaching when you are explaining to your students the concept of work from a thermodynamics point of view? That's the specific question that we are trying to address here. Yeah, please go ahead.
I emphasize the students that what is the sole effect external to the things in the system. Like if a fan is running inside the room, what is the effect external to the system when we are inside the room? So by this example or lots of example, we can teach the students and give the examples to understand about the work.
Can someone else comment? There are a few raised hands. Dr. Salil Ismail, then Dr. Piyush Vanjara.
Yeah, good morning. Yeah, I would like to add that normally the students, when they learn about the work, they have a limited sense that they will be learning, like for example, force and times distance and that kind of thing. Whereas in thermodynamics, as per our definition, it is having a much more wider connotation. Like for example, the electric power supplied, that can also come under a category of work as per our definition. So that complete definition, like I think a previous speaker was telling, like comparing it with the sole effect of having weight being raised. So that broader definition, I think we need to convey. And yeah, using whatever examples I think have been given in the video, for example, those will be quite useful to give that wider interpretation to the concept of thermodynamic work.
Okay.
And I think that sign conventions, those are also very important and interesting to look at. So I think that.
Okay. Dr. Piyush Vanjara, please.
Sir, when we introduce work to the thermodynamics students in the class, they do have a feeling of work which is actually a primitive property as per our definition. So and they are having the base of physics in their mind. So, and similarly, the work is very important property in the thermodynamic itself. So our main task in the initial phase is
So, Dr. Vanjara, let me interrupt you for a second.
Yes, sir.
I would resist, or I would desist rather, I should say, using the word property when it comes to description of work, because property in thermodynamics has a very specific definition.
Yes.
Work is an energy interaction as right. Okay.
That is
also has a reason. Let me request him to go ahead. Then you can continue, please. Yeah, go ahead. I thought Professor you had raised it. Yeah, go ahead.
Okay. Sir, so work and heat are actually, precisely speaking, energy in transit. So our main task is to for the students to connect them with from a primitive base of work to this particular aspect in thermodynamics.
Yes. So that is what has been the objective of these specific 3 lectures, 4 to 6, where the primitive notion of work has first been described, and then as Dr. Salil Ismail said, the notion of work has been expanded, and then the thermodynamic definition of work has been brought forth. Yeah, fine. Professor Shahbaz Memon.
Good morning, all.
Yes, please, go ahead.
Sir, I generally go by defining energy interaction between system and surrounding, or two systems, in a way that there are 2 types of energy interaction. One is because of temperature difference, which we will call heat transfer. Any other energy interaction between system and surrounding, which is not because of mass interaction, will be work interaction. Simple.
Yeah. So here in our way of developing this subject, we haven't really defined heat interaction at all so far, and in fact we will defer it only when we bring in the first law of thermodynamics. So you will see what we mean by this, that we haven't really defined a heat interaction right now at all. So presently we are just focusing initially on defining the work interaction.
Okay, sir.
Yeah, so there is a good comment in the chat box by Narain. So that's a useful one. Yes. So that's in fact something that we also keep emphasizing, that the raise of a weight in a gravitational field is what needs to be the eventual effect, and that raise of the weight is something that we keep emphasizing. That's correct. So going a little further, let me pose this question. Did any of you, of course, the definition of work as an energy interaction that can be completely reduced to the raise of a weight in a gravitational field is something that we often see in many textbooks and so on. So that is fine. However, this notion of the operational definition, as has been introduced in these lectures 4 to 6, in order to expand the notion of work, is something probably that is worth discussing, in the sense that this operational definition and the process involved in that operational definition is something that you may want to think about. and it'll take some time for each of us to follow it in a very clear manner. But once it is done, it becomes very useful, and that's what I also wanted to point out. I think Professor Bhandarkar is here. Let me ask him to comment on that if he can.
Yeah, so I think someone said that they would like to first define the heat interaction, and they defined it in terms of temperature. So then the question would have been, how do they define temperature? Okay, and that becomes slightly critical, because I don't know how. I want to know. I think, was it Professor Memon who talked about defining the heat interaction first?
Yes.
So can Professor Memon then comment how he defines temperature? Yeah, because this becomes critical. We see, and even reasonably standard textbooks do this same mistake, that they define the heat interaction in terms of the temperature, and when it comes to the temperature, they define it in terms of the heat interaction. Okay, and we do not want to fall into this trap, and that's why we said, if you want to avoid confusion, you need to be consistent with your arguments, and you need to first define one of them properly, okay, which doesn't involve anything else, okay, and it should involve only primitives and nothing else, and then you can define the other one very well, depending on uh, how you want to go about it. Now, of course, someone seems to have commented that there are two modes of energy interaction: one is heat and one is work. And you should realize this is entirely our definition, okay? So we have decided to define something called as the work interaction in very precise terms, and everything else we just put in one basket called the heat interaction. And you must try to think slightly more and realize that this was never necessary, okay? It is just a matter of convenience that we have done this, and it helps us a lot. Okay, and I would like the faculty here to think slightly more on that we have put every other interaction in this basket called as the heat interaction. Okay, so anyway, I'll let this conversation go, but I just wanted to emphasize that please do not fall into this trap of the circular definitions. Yeah, thank you.
Just to emphasize again the point that Professor Bhandarkar was making, we build on things. So we start with the primitives that we are aware of, and using that, we first talk about work, and we come up with a very precise definition of work. And then once this energy interaction called the work is defined, then we go on to do something else in terms of that. So that's what has been found to be very useful in terms of logical progression of the material, and also not getting caught in this circular argument which he was mentioning. So Dr. Salil Ismail, let me try to answer that comment of yours related to open system. The way this specific set of lectures on thermodynamics have been developed is that for almost 3/4 of the semester, or even a little bit more, everything has been developed with respect to a closed system. So we develop the notions of work, heat interaction, and then first law, heat interaction, and second law in between, zeroth law, and so on, exclusively restricting ourselves to a closed system. And once all these notions are correctly and clearly understood, then we take up the development of the corresponding forms for the first law and the second law and so on for open system. So what has been found is that once the notions of first law, zeroth law, and second law have been very well understood by the students, the extension to open systems is relatively straightforward, and we do it at the end of the class. So that's something different that you will see from standard textbooks, where they will introduce typically the first law and talk about the first law as applied to closed systems, and immediately then the first law is also explained or developed for open systems. In our scheme of things, what we have found is developing everything for closed systems initially, and then toward the end taking up the extensions to open systems has really helped the students. And at that time appropriately, and you'll see that part will be hopefully taken up in the session tomorrow, the flow work and so on will be appropriately included when we extend the first law statement in particular for open systems. Let me ask Professor Bhandarkar to quickly comment on that.
Yeah, I mean, I think it's best not to talk about open systems initially, and then there's no point in talking about won't there be an energy interaction. Of course there will be, but that is purely because of something coming in and out. We are not talking about that interaction at all. So it's best just to talk about the closed systems initially, develop every possible understanding about the closed system, and then move on to open systems, and then we will not even try to get into such questions, because the second part of the question is something that absolutely we do not encourage in our kind of discussions. Okay, that just leads to confusion. Thank you.
Yeah, so what we are hoping for is the lecture material, all lecture videos will be always available to you from now on. I suppose the workshop staff can comment on that, but the idea would be that after these 3 days are over, you can sit quietly and sort of think about how this entire material has been developed, and then hopefully realize that okay, certain things do make sense in this manner to go. Of course, this has all been done based on the student feedback over so many years, and this is how we have come to realize that students seem to understand this succession quite well. So one exercise that we normally do, and I think Professor Bhandarkar will agree with me on this, in class is once that operational definition of work has been brought forth and explained, the process of applying an operational definition of the examples which were discussed earlier, and I'll quote at least 1 or 2 examples of those. So there was a rod which was getting either pulled or pushed. Then there is a battery which is getting discharged or charged. Then there was a stirrer which was stirring a liquid. And of course, there is the most classical example of gas in a piston cylinder assembly, undergoing expansion or compression, whichever way you want to look at it. So these examples of work, which I think the students are quite familiar to identify from the primitives, so to say, can then be taken up, and the students can be asked to think about how they can apply the operational definition of work for these specific examples to improve their understanding of it. I think this is how we normally spend some time in one class at least. So, Professor Bhandarkar?
No, yeah, that's perfectly fine. I think that's how we go ahead with it. So I don't have anything more to comment.
Okay, fine. Yes, so there is a comment on one-way and two-way modes of work, and that's something that probably was not seen by some participants, at least this terminology, I should say. The first and foremost thing is that in case you wish to introduce this in your course, please make sure that there is absolutely no confusion of one-way or two-way mode of work with this reversible notion. Okay, so these are absolutely two different things. Reversible has nothing to do with one-way or two-way modes of work. So that's something that, again, to teachers we would like to point out. Now, to students anyway, the way we develop this course, we never anyway talk about the reversible process or reversible work or whatever at all till we introduce the second law. So in our scheme of things, one-way and two-way modes of work comes in while we introduce this work, and it is fairly straightforward in terms of understanding by the students. Yes, so I agree with you, Achintya. It is not really seen commonly in standard textbooks, and it turns out that it's a very, very useful tool, in some sense, for developing further ideas. Yeah, Dr. Vanjara, please go ahead.
Yes, sir. So I think it is needed to clarify the difference between the reversibility of a process and this one-way, two-way interactions. So the students and we ourselves should not get confused between that. And that was actually explained very well by giving example of expansion, compression, as well as charging, discharging.
Yes. I think that's very useful, and one may have to spend a little bit time on that in the class, but it's worth doing that.
Yeah, because that actually gives us a new concept that is rudimentary.
Yes, exactly.
Yes,
Exactly.
and I have seen that that rudimentary concept which gives me number of properties required 0, which actually leads again to the definition of the temperature. So in that context, it becomes very important.
Yeah, it's a very useful thing to incorporate. Yes, I agree. So those are, I think, the most important aspects related to work interactions that we. There is a question here. One of the best method to understand the concept of thermodynamic work, and in fact, this is what we think the lectures do it. The notion of operational definition and how to implement the operational definition to classify whether a certain energy interaction is work or not is perhaps the most comprehensive way of explaining the concept of thermodynamic work. So, Professor Bhandarkar, do you want to add to this at all?
Yeah, I think the operational definition it involves taking two systems, and again it comes back to this question that someone had asked yesterday, that why is the surroundings taken as system B? I mean, and Professor Gaitonde had clarified, that oftentimes we just think surroundings and everything else outside. Okay, and that is a common notion that has been put in many textbooks, and we should realize that interactions are between two systems. The other system also should get a proper boundary, and then we discuss the operational definition specifically in terms of two systems. And I think the way Professor Gaitonde introduces the system A, B, and the interaction he calls I, and then it is a very logical way of saying either A does work or B does work, depending on who is capable of raising the weight in this case. I think that is, in a series of steps, you actually explain things reasonably well, and each of the earlier definitions, standard definitions or primitive definitions of work, are just incorporated neatly into this definition, and hence there isn't any ambiguity any further. So I think this is a really good way to go ahead. Thanks. I mean, Professor Gaitonde, of course, can comment more on this.
But there is one comment immediately that since we are in live session, please give at least one example. So let me try to answer that in a slightly roundabout way. You can consider the example of gas in a piston cylinder assembly, let us say, and then the gas is at some pressure, let's say 2 or 3 bars, and the outside, which will be considered as another system, if you wish, is at 1 atmosphere, 1 bar, let us say. And now there is an expansion work that is going on if the gas expands by pushing the piston out. Now here is where we would like to implement that operational definition. So first we need to define the system correctly and carefully by specifying proper boundaries to it. And in this case, I will say that the gas that is contained in the cylinder, bounded by the cylinder walls and the piston face, is identified as the system under consideration for us. And then everything else is system B. Okay, so including the piston that is getting pushed by the gas by the system. And now you can imagine replacing that system B, okay, which includes the piston and whatever else that you wish outside, with a suitable contraption that you can think about bringing from your primitive mechanics or whatever else, physics, and see whether that expansion process can then result in a raise of a weight using a, an intermediary which is now going to be replacing system B, okay, and see whether this whole thing can result in a raise of a weight. If you can demonstrate something of this to the class, that if you come up with a pulley system, for example, which will replace system B being the piston and so on, can it result in a raise of a weight? So if you are able to show that, then we can conclusively point out that system A, which is our gas in the cylinder, is doing work on system B, which is the piston and everything else outside. This is one example that I can quote, but you can always think about that very first example, which is, let us say I have a rod, okay, metal rod, let us say, in some sort of a cantilever type fashion, and the free end of the rod is being pulled by an external force. Here is where you can think about how to define a system, okay, calling that as system A, how to define everything else as system B, then replacing system B with a suitable contraption from primitives, and to see whether this pulling or pushing of the rod can result in purely a raise of weight in a gravitational field. If you are able to show this, or if you can elicit this from the students, that you ask them, can you think about coming up with a contraption based on only primitive understanding, that this situation, this energy interaction will lead to a raise of weight. Okay, so that's another example. And so same thing you can repeat for charging and discharging of the battery, or even this stirrer in a liquid bath, and so on. So let me here request Professor Bhandarkar to comment on this.
Yeah, I think maybe I am not sure what example was needed, but you should realize that in the piston and cylinder system, depending on, let's say you call the pistons, the gas within the piston as system A, then depending on the pressure difference, you can figure out which is the system which is capable of doing or raising the weight, okay, if the other system was replaced. So you realize that in certain conditions A can do the work, in certain conditions the outside, or the system B is doing the work. But if you look at the stirrer system, you realize that the stirrer can stir the system, okay, but in return, okay, this let's say you have again a gas in a piston cylinder system. You have a stirrer, you can stir the gas in the piston cylinder system, but the reverse cannot be done. Okay, so whichever way you try, you cannot do it. So this becomes now a one-way system of work, where only, let's say, the stirrer is system B. The stirrer can do the work, system B can do the work, but system A cannot do work on the stirrer. So this now is our one-way and two-way modes of work, that if A can do work on B but not the other way around, then you know what we mean by a one-way and two-way. Yeah, thank you.
So TKG classes, my request would be that since we have limited time, we will not be able to go to every example and discuss it in this live session. My request would be to please go back to the video and look at it. But the idea is as follows. Let me at least point out the idea there. Let us say that I define the rod in that specific example as my system, and then there is some other system which is exerting a force on it. Let us say that force can be either tensile or compressive. It doesn't matter, one way or the other. You can keep the analysis going. And now, having defined that rod as the system, then you can start thinking about whether that system is capable of doing work, or work is being done on that system by some other system, which we are going to be calling as system B. That system B in this case is the one that is exerting the force on our system A under consideration. Okay, and then you can try to bring in the idea of the operational definition of work. And once the once you realize that who is capable of doing work on whom, you can try to replace one of them with a suitable contraption and see that this energy interaction will then result into a raise of weight. In that sense, you can try to bring in the understanding of what thermodynamic work is in this with respect to this specific example.
There seems to be a question by Surendra Jangu. The first part of the statement, both parts of the first statement is never mentioned and is not true at all. So I'm not sure where he got the statement.
Correct. Yeah.
Good morning, sir.
Yeah, please go ahead.
Sir, actually, I just want to have one question regarding the work transfer.
Yeah.
So, as I just understood that something which can be equated in terms of raising the weight can be called as the work transfer. So, if the same concept is applied in space station where the gravitational force is not existing, and let's say the same example of piston cylinder assembly, and inside that there is a gas, then how we can define the work?
Yeah, so you should be clear that if there is no pressure outside, then there is zero work. So it's very straightforward.
Yeah, so fundamentally, the work in that specific case, when you have a piston cylinder assembly with some gas inside, and there is an ambient, let us say, or environment, and that corresponds to a certain pressure. If that pressure is zero, then there is no work that is done by the system, really. So, yeah, Professor Bhandarkar, you want to answer that Naren's latest question? 9:30.
Yeah, sorry, that's an open system. We will deal with that later.
Exactly.
There's dynamics involved. Yeah.
No, that's fine. So that is what I also wanted to mention. Naren, presently what we are talking about is closed systems only, and the different types of work interactions that have been identified are with reference to the closed system. The one that you are mentioning comes under open system, and when we go to open system toward the end of this workshop, that part will be addressed. So let's please wait.
Yeah. So Professor Puranik, so if can I just add a statement here?
Yeah, please go ahead.
Now, so my understanding is it's we know as instructors probably this is an open system. So I'm again bringing back to the pedagogy. So this is the first time I'm telling this example to the student as an instructor to the student. But as we tell, the student will construct in the mind, because if
correct. So sorry.
So we might tell, in a stirred vessel, the stirrer rotates and it churns the liquid, and the other way around does not happen. But immediately we might have students who will think of a situation what they have seen, or in some other by their experience they will say that no sir, in some other case the liquid also rotates the stirrer. Right, so I just want your inputs on, if we face these kinds of questions, which is indeed good, the student going ahead with our observation. Now, how to deal this in a very elegant fashion rather than just telling wait, I will come sometime later and then make this concept. That's my crux of this question. It's not for the instructor; it's for the student to gel with that concept.
See, here in this specific case, when we have a still liquid, let us say, in a vessel, let's say, and then there is that stirrer. I think in the lecture itself, Professor Gaitonde has asked this question. So, is there any way we can ask that liquid to try to rotate the stirrer? in this specific situation when I have a still liquid, contained in a vessel, and I just simply suspend a stirrer in it, let us say. If I am able to rotate the stirrer by external means, obviously I am doing work on the liquid. But is there any way in which the liquid can rotate the stirrer? That's the way you can try to pose the question to the students and point out that when they say that liquid is doing work in some other situation, these situations are different. They are not really comparable. And that's the reason we said that when we go to open systems, when there is a flow of liquid involved and therefore there is that flow work involved, is what we can point out why the liquid or the fluid will end up doing work. Before you say anything, let me ask Professor Bhandarkar to also comment on this.
I think I just wanted to say that it's back to defining the system. So once you have defined the system and its boundaries, it becomes very clear what system we are talking about. So I think maybe in this respect, you must tell the student, first define the system. If this is the system, can it do this or not, is the question that we pose. In some other system, definitely you can, probably do something else. But in this current system, which is just been defined as A with a proper boundary, etc. Can it do this or not is a question that we need to ask. And as long as we are, clear about this question, I think, and the system, then I think the matter is resolved. Yeah, I think Professor Kaitonde wants to add.
Yes.
Now, Naren's question is good. But now that we are in a group of teachers, I may bring up the fact that when I am confronted with a student and a question, my response quite often depends on the background of the students. For example, if he's not that good a student, then I will say, see, this belongs to an open system. We will consider it when we consider two open systems. But then a good student will need at least part of the answer almost immediately. And for such a student, we have to then say that, look, we have to go in more detail. Remember, quite often a misnomer comes that a movement of a piston is work, but rotation of a shaft, because stirrer is a shaft going into our system with some blade or something on, is not a two-way work. That's not true. If you have a turbine type of a system, that tau d theta, that is the rotation against a torque, can be a two-way mode of work, because we can have a pump type of system where the work is done on the system, and a turbine type of a system where the work is done by the system. Okay. Now, some student may, a really smart student may come up. He said that, look, suppose I have a reasonably dense liquid which is already stirred and hence it is still rotating. And if I put a stirrer in it, then the liquid which is already rotating and being swished around till it comes to a stop is likely to rotate the stirrer. Then the answer here is yes, but then the system which we are considering is not in an initial state of equilibrium. And as we proceed, you will realize that one of our premises is that an isolated system which is not in a state of equilibrium will tend towards a state of equilibrium. If isolated system tends to do that, there is no reason why a non-isolated system can also tend to do that. And while doing that, it can, if there is a possibility of interaction, it may lead to an interaction. But that is a process which in our simple thermodynamic situation, we are unable to analyze unless we go into more details, because the initial state is not a state of equilibrium. Now, this requires a student who will appreciate this. If a student is going to get more confused with this, better not use this approach. Thank you.
Yeah, perfect. So that's what I just want to hear. What could be the different response that you might have given your long period of taking the course. That's all, right?
Yeah, talking between teachers, this is important because,
Yeah.
A good student, a topper student who appreciates thermodynamics, at least up to that level, will require one kind of response.
Yeah.
Otherwise, a student will be put off.
Yeah.
Whereas
Yeah.
a routine student who is curious but wants to learn but may not be able to appreciate the nuances, we can say wait a few lectures, a few weeks, then automatically this will get explained.
Yeah, perfect.
Thank you.
Thank you.
So let me try to move on here, in the sense that we want to try to cover a little bit more now, and so with the definition of the thermodynamic work, with the help of this operational definition and so on, then we introduce normally this first law. Okay, and as you can imagine, so far there is no mention of Zeroth Law. And again, repeating the same thing again, that this is a sequence that we have found students do appreciate in terms of understanding the material. You can of course think about whether this is the way to do it or some other way can be utilized. But having done this definition of work interaction, now we go to the next step and we introduce a specific form or statement of the first law of thermodynamics. And in the lectures you must have seen, it is called the Carathéodory's statement of the first law, which essentially generalizes the behavior of adiabatic systems. So now we introduce the word adiabatic, but then immediately define it based on what we have developed so far, namely work interactions. And then we essentially say that an adiabatic system is a system where only work interactions are permitted. So with these two things, then we go ahead and introduce this Carathéodory's version of first law. And again, I think it's been well articulated in the lectures that there exist different versions of the first law of thermodynamics, and later also for second law. What we have done here is that with reference to the logical progression that is going on, the most appropriate form of the first law has been utilized as the introduction of the first law statement. Okay, so let me ask Professor Bhandarkar to also now add to this.
No, I mean, I don't think I have much to add here. It's just that people should understand that we have just chosen the most convenient statement, which is allows us to be consistent. So if someone can come up with a different system, they are free to do so, but you should just keep in mind that it should be consistent. It's not that we dictate that this should be the only way out of the whole thing, but it's just a way we tend to adopt a series of steps which is consistent. So that's all I would like to add on this.
But it is instructive to perhaps know from now other teachers here. Correct. So that's precisely what I was getting at. So in fact, Dr. Vanjara has sort of answered my question already. That to me also, when I took this series of lectures first as a student, I realized that this is not how most standard textbooks that we tend to open and see are introducing the first law, and which is what I think is getting corroborated by Dr. Vanjara and Dr. Anandan now. So the question would be then, if you want to do it, if you want to introduce the first law in this fashion, do you think that you will have a lot of trouble in getting the students understood this, or you think that this sequence and this way of doing things will work? That's the question. Yeah, Dr. Anandan, please go ahead.
Yes, sir. First of all, I would like to thank Professor Uday Gaitonde for very good, as far as I am concerned, it is, as a student as well as a faculty handling thermodynamics, this way of introducing first law of thermodynamics to the students, it is unique and nowhere we have so far, as all are aware that we have not mentioned about heat. The moment we say adiabatic, the first thing it comes to my mind so far, I mean till yesterday, till today early morning was heat. When we mean to say adiabatic, it is no heat transfer. But the other way around, I have learned something new from Professor Uday's, watching Professor Uday's lecture videos, that the different form of defining adiabatic. Thank you very much, sir. And I wish to learn many more things from the another couple of days of this program. Thank you.
Yeah, so the use of this way of doing things is then that we can then introduce a non-adiabatic path, let us say, going from state 1 to state 2. And then the heat interaction is defined as the difference between the work that will happen when I go from 1 to 2 in a non-adiabatic path and the work that will happen when I go from 1 to 2 in an adiabatic. So this is the way the heat interaction has been now introduced as another energy interaction. Remember again, to define the heat interaction, we have not used the notion of temperature at all. In fact, till now, there is no mention of temperature absolutely. So that's something that we wish to point out is, perhaps a little different from what you have seen as standard textbook material on this. And of course, the moment this has been done, you realize that if I choose that path going from say 1 to 2 as again an adiabatic path, then obviously by definition, the heat interaction for such an adiabatic path comes out to be equal to identically 0, the way it has been defined, which then of course doesn't violate any other notion that one had about an adiabatic process. So that's something that we wish to point out here. Professor Bhandarkar?
Yeah, I think this again goes back to the same question raised about pedagogy, that students have been exposed to heat transfer earlier in 11th and 12th, and they would then come and ask, why is this so different from what we learn, because all regular textbooks in 11th and 12th have a different definition of how heat transfer is, whereas as Professor Gaitonde has already mentioned in the chat, okay, the form that we are using, the Carrier-Theodori form, is more than 100 years old, and it has many textbooks use it in a very standard fashion. Okay, but the fact is that our high school textbooks do not do that. And as a reason, whatever I think Professor Naren had pointed out, that question is bound to come. Students are going to ask, but we learned this so differently. But somewhere you will have to tell them, forget those definitions. Those are, I mean, it's not that they would be incorrect. Finally, we will show what may be more accurate. But if you define it in this way, you will be more consistent, and there will be less confusions later on. So it's best to unlearn some of those definitions, and I think it comes later on, but two of the definitions which definitely students need to unlearn, which are related to this heat transfer concepts, are this concept of CP and CV. Okay, so I think these four definitions, or rather heat transfer, adiabatic, CP and CV, I think these are 4 things we must tell students that whatever they have read up till now in 11th and 12th, they better forget it if they want to, go through this course without confusion, because those definitions only add to the confusion. That's all I need to say. Thanks.
Yeah, I think there is also a notion of conservation of energy that is associated with first law. And that's something that we don't talk about at all. So we talk about introduction of this first law using this Carathéodory's statement, and what we are really talking about is a system, another system that it is interacting with, and the energy interactions that happen are of two types. One is the work interaction, which has been very precisely defined. And now that with the Carathéodory's first law statement, we bring in this idea of adiabatic work, then introduce the idea of course, heat interaction as the difference between work interactions if I go as a non-adiabatic path and an adiabatic path, and so on. So this is the way we try to sort of progress in the scores. So with reference to what I was just saying, any comment on using the words law of conservation of energy when it comes to the first law, now that you have seen the first law getting introduced in a manner that probably you had not seen earlier, or some of you had not seen earlier? So we'll come to zeroth law little later, after the first law is over.
Yes, sir.
Yeah, so there is one comment which I will comment on by Vednath Mathur. The sign convention, for heat added and so on, is reversed, and that depends on what sort of, I'll say that how you learnt it, and that's absolutely fine. Okay, so the only point that we want to try to convey here is that whatever sign convention that you introduce, it needs to be consistent. And consistency is the key here. It doesn't matter even if you define the sign convention in a different manner, but then you have to be able to stay consistent with that and then develop the further subject. Since Professor Gaitonde has a raised hand, let me request him to go ahead.
We should understand that we have sign conventions everywhere. Even, in our coordinate geometry, what we by default considered a positive x direction is by convention towards the right. There is nothing wrong if we take it towards the left. That's all. Even up to the first law, we already have 3 points where we have decided on a convention for signs. One is the work interaction. The second one is that W minus W adiabatic is defined as Q. That is the heat interaction. And the next definition where sign convention will come in is the change in energy.
So, Dr. Vanjara, the sign convention for the heat interaction gets defined automatically once we have defined the sign convention for the work interaction. That's the way it works here.
Okay, sir. Sir, but we have, I think, in the lectures still not introduced any heat interactions sign convention.
That is what I'm trying to point out. We have defined the heat interaction in terms of the difference between work interaction when the system goes from state 1 to 2 following a non-adiabatic path, and work which is involved in an adiabatic path. So the difference between these two has been introduced as the heat interaction. But at the same time, if you remember, just before this, the adiabatic work, because then it is immaterial of the path, has been also pointed out to be a point function. It's not a path function. And the notion of energy is introduced using that. That's what really is something that we didn't talk about. So formally what we do is we write delta E as E2 minus E1 equal to minus of that integral 1 to 2 of the adiabatic work. And here is where we have introduced the sign convention. And maybe I'll request Professor Bhandarkar to quickly comment on this, why we introduce it in this fashion.
Which one? I didn't get it. I mean, it's just a convention. We decide what is possible.
Yeah, so there is a notion of, if a system does work, the system will feel gained of energy. That's the kind of primitive notion that we have. And to be consistent with that notion, we have introduced the sign convention in that.
Sir, may I?
Yeah, go ahead.
Sir, the advantage which we are getting by this sign convention, which actually earlier in the books of chemical engineering was also used, that it helps to understand the first law of thermodynamics also, that as it is explained that the change in the energy will be equal to the difference between the heat and work interactions. But later on, the sign convention was changed, keeping in one perspective in mind, that generally the heat rejected by the system, means from one system to another system, is taken as negative. So to make it consistent with the heat and work interactions, like this, considering like from one system to another system, it is taken as negative. That's another that advantage in the another sign convention.
But that's the same thing that we use here. If I have my system under consideration as system A, let us say, and if it rejects heat, then that is automatically given the sign convention of being negative here as well.
Yes, but sir, if heat is going out from system to say another system or surrounding, whatever we say, if we take it as negative, the work done by the system here we have taken positive. That actually again the different than the sign convention. So that's what my question is, when somebody has put up a question that was the sign of action. I don't change only the heat notations are mostly saying all the textbooks that heat rejected by the system when it goes out, it is taken as negative, which we have not reversed over here.
Okay, Professor Bhandarkar, do you want to comment on this? I don't understand exactly what the question is.
Yeah, can you repeat that? Sorry, even I didn't get. What is it that you said?
Sir, if work done by the system, then it is taken here positive. Yes. Okay. And say heat rejected from the system, from a particular system, then generally I think we do take it as negative.
Yeah, if heat is rejected by the system, our sign convention is such that it is taken as negative. Yeah.
Okay, and that is, I think, sir, consistent.
Yes, it is
everywhere.
consistent.
I think.
Yeah.
I think in no textbook.
Yeah, that is consistent.
Yeah. That's why what I have asked actually at 9:59 that that there was one question posed by Vednath Mathur that the heat sign conventions are changed. I think we have not changed the heat sign conventions. It's only in some textbooks.
Yes.
It's only in some textbooks that work. Yeah.
No, when the student come to us after reading physics and chemistry in their first year classes, so in physics and chemistry,
Yes,
they have been taught that the heat added to the system is termed to be negative, and heat rejected by the system is positive. So he has in his mind that kind of convention, so which he had studied in his science classes, physics or chemistry classes. Now in thermodynamics, it's reverse. So it's sometimes I face this challenge to reverse this understanding among students, means to unlearn
yes.
this.
We understand that actually is indeed a valid point. And the only way to address it is to sort of keep pointing out that as long as the set of conventions that we are following are consistent, it is fine. So even in chemistry, if you go ahead with that set of convention, and as long as they are consistent as you develop the subject, it is fine. And we do the same thing here. We point out that this is the convention that we introduced, and we stick to this going further. So it's maintained as a consistent set of sign conventions. But I understand. I agree.
Yeah. Hello.
Yes. Go ahead.
Sir, recently the sign conventions which most of the chemical engineering students and the faculties are using, that is anything from system to surrounding is taken as negative, whether it is work or heat, and the reverse is positive.
Okay, that's Professor Bhandarkar, do you have a comment on that?
I was not aware of. I was only aware of a sign convention which the chemists use, where the work interaction sign was exactly reversed. But this is new to me. Maybe, I mean, as long as you are consistent with how the law is stated, I don't see a problem. But, I think different conventions, the problem is, everything we do in a certain way so that there is less confusion. Now, if different people use different conventions, it can always lead to problems when two different people are talking. It's just like if I talk in meters and you talk in inches, we are still talking about length, but it can still lead to confusion. So it may be better to, I can only comment that it may be better to have a single convention all throughout. But if people want to do differently, I don't know what to do. But as long as at least they should be, ensuring that and there is no inconsistencies in how they apply the laws. I think that probably at least that is sufficient right now.
Yes, sir.
Yeah, but sort of the most important summary that I would like to provide for this first law discussion is the hammering of the notions that Professor Gaitonde has a good comment. It is indeed unconventional, but yeah, fine. That's fine. It depends on where you are coming from. Yeah. So going back to what I was saying, it is the energy interactions as work interaction or heat interaction is what we keep on sort of emphasizing to the students, and it goes in a certain progression. So first we define what is a work interaction, then we state the Carathéodory's version of the first law, and then bring in the definition of heat interaction without resorting to the use of temperature in any manner. So that's what at least I wanted to point out to this set of participants, and with a request that think about this way of doing it, whether this will try to minimize any confusions that your students may have in understanding and following the subject. So that's really the bottom line comment from my side at least. Yeah, Mr. Junaid, please go ahead.
Sir, while introducing the first law, one of the most you can say common and important method is also Joule's experiment, explanation of Joule's experiment, and with the help of that we can come up with the first law. Any point on this?
Yes, actually that's a very good point, I will say, and in fact Professor Bhandarkar I think is a better person to address this question or comment, so I'll request him.
So when you are talking of the Joule's experiment, how do you, do you introduce it in class?
Yes, sir. Yes, sir.
So how do you explain it, and then maybe we can, let's see how you connect it, and then maybe we can go ahead with that.
So with the help of that experiment, actually, I was referring the lecture notes of Professor S.K. Som from IIT Kharagpur. So I just found it was very well explained, like in the way we can come up with the summation of W equal to summation of Q, and in that way we can introduce in official way the first law. You can say one outcome of the first law.
Okay, in this case, I think I would rather have Professor Gaitonde comment on it, because the way it is portrayed, that I have some reservations, but I think maybe he can. Professor Gaitonde, can you comment on this? Yeah, that is true. For me, it's just a convergent term. So now, if this has been brought up, I didn't know how to answer this.
Let me say something about Joule's experiment. Joule's experiment is one of the most famous as well as one of the most misunderstood experiments. Misunderstood to such an extent that even good physics textbooks have that misunderstanding clear in their exposition. If you go to the original paper by Joule, which is archived in many places, you will find that there is no heat interaction involved in Joule's experiment. It is only the change of state of whatever his system was, and the interaction was only work interaction. Okay? And we seem to remember only that lowering of a weight, stirring that thing as the interaction. If you see, Joule did lots of experiment and he came up with his idea of first law. Today we consider Joule's experiment as something which hinted at first law, but actually it is an experiment in which we can today purely say that it was an experimental attempt to measure what we today call the specific heat of water. Okay. Unfortunately, specific heat is again a nomenclature or a terminology which is handed down from history, and you will soon realize as we proceed that well, the specific heat has absolutely nothing to do with the heat interaction. It can be related to the heat interaction to the first law, but the current definition of specific heat, whether at constant volume or constant pressure or any other definition, has nothing to do with the interaction heat. So with due respect to Professor Som, the late Professor Som, a good friend of mine, and all others who have attempted to define first law or derived first law from Joule's experiments, that's not really true. The first law is a generalization of our understanding, not just based on what Joule did, but based on many other observations, all of which now are consistent with first law, because it's a generalization. That's it. Thank you.
Yeah, so there is a comment here from Dr. Vanjara that we need to discuss the sequence of laws to be introduced in class, and this is what we have been saying over the last day or so, is that the sequence that we follow here, which is the first law first, then we will introduce the zeroth law, and then eventually go to second law, seems to have worked in the sense that the students seem to follow this sequence quite well without getting confused. In fact, historically, this is not how things developed, and I think for those historical comments, let me quickly ask Professor Bhandarkar to spend maybe a couple of minutes on that.
No, I don't think I have much to comment here. It's just that again, at least in our method, this is consistent. But there is no harm if you devise a method where you state it as the second law first, then the first law, and then the zeroth law. But you should find out a method which is very consistent. And Professor Gayatri will tell you that based on if you are very mathematically oriented, then you can actually start off with a definition of the second law, which is totally consistent, and then move on to the other laws. Okay, and I mean, any order is fine as long as it's consistent, but then that argument has to be very consistent, and there should be no circular definition. So in our present case, this seems to be the most easiest way to talk about the first law first, then the zeroth law, and then the second law. So that's all I have to add right now.
Yeah, so in fact, Professor Gaitonde has mentioned quickly that developments related to or thought processes related to the second law came first, and then the first, and then the zeroth law. But let me try to address one question which I think is important, because students are definitely posing it, I suppose, and that is if there is any proof for this first law. So see, there is no proof, in the sense that you cannot prove first law with some further basic businesses and so on. That's not how it is. It's just that these laws, whether it is first, second, or zeroth, here in this case of thermodynamics, are what we mentioned yesterday. They are basically formal generalizations of how nature behaves, and these generalizations have evolved over a period of time. As we are discussing, certain different ways of putting forth the first law also do exist, depending on the person who was trying to generalize in a manner. But there is no proof. I mean, the only way that you keep pointing out to the students in these situations, there are laws of nature. That's precisely what the point is. And what we essentially keep pointing out to the students is that there is no evidence that any of these laws has been violated ever. And that is all that really is, we need to point out. So there is no proof per se, but there is no contrary evidence at all to what these laws have stated. And that is what I think one can, point out about these laws. And, I will say that it's the same with Newton's laws of motion as well. Okay. So there is no proof per se for Newton's law. It's just a generalization of observations on how nature behaves, and that's all needs to be clearly pointed out to the students.
Sir, I have one
So-
question.
Yeah, please go ahead.
Sir, traditionally we are telling that law from first law of thermodynamics while we are explaining to the students law of conservation of energy, and sometimes we are using. Is it correct or not? I don't know. That is, work and heat are mutually convertible.
That's a very good question. I think the same question has been posed by Dr. Vanjara in the.
And moreover, you are telling that from what is that? Really, it is a very strange thing for me, sir. What about the Kara-Theodor is a form. So if it is that case,
So
what if adiabatic system heat transfer is always zero? Like then the W is equal to del U or del E.
That is correct. The reason you are able to say that is because you already knew, what is meant by a heat interaction and so on. So that is why you say that, okay, what is the difference here? There is no difference here. However, you think about a student who has entered your class and who doesn't really have any formal understanding of, heat interaction. He or she may have some idea based on their previous curriculum that they have gone through. However, the formality of defining the heat interaction is something that I think is better done in this fashion, is what we think. The difference between non-adiabatic work and adiabatic work. And this is how I think I'll keep, repeating in some sense that it turns out to be a situation where you will create minimal confusions later. Now, as far as your question on whether to call first law of thermodynamics as law of conservation of energy or not, the answer really is that we want to try to point out to the students that the first law necessarily involves energy interactions. Okay.
Yes.
And therefore, very carefully, a work interaction has been defined earlier. Then the first law statement of Kara-Theodori has been brought in to point out the nature of how adiabatic work transactions are, and then the notion of heat interaction has been introduced. So in that sense, if you see, there is no mention of conservation of energy, these words at all. So this is what I will keep saying, that there is no need to mention these words.
Yes, sir. Yes, sir.
That's what my take on this is. But let me ask Professor Bhandarkar to comment.
Yes, sir.
Yeah, I mean, you should keep the two statements different according to me. And of course, you can show that they are equivalent. There's nothing harm in it. But, the law of conservation of energy as it is stated in high school does not have energy interactions. It is just talking about interconvertibility of energy forms. Whereas this is an interaction, it requires two systems, it requires energy crossing the boundaries, and this is not part of the regular law of conservation of energy. That is why you must necessarily keep this different initially. Yeah.
Sir, then that is sometimes we are using cyclic integral of dq is equal to cyclic integral of dw, and q minus w equal to del E. How we where we use these two?
Yeah, so that cyclic integral is applicable for a very specific process called a cyclic process. So we first, define the cyclic process very carefully. And we say that for a cyclic process, the initial state and the final state are identical. Okay, so if you call initial state as 1 and final state as 2, 1 is equal to 2. And because of the fact that we have introduced the notion of this thermodynamic property called the energy, when we introduced the Kara-Theodori's statement of the first law, we point out that the change in this property called the energy has to be necessarily equal to 0 if the initial state is equal to final state. And therefore, it follows that the work interaction for a cyclic process must necessarily be equal to the heat interaction for the cyclic process. And the convention to sort of represent this is through that cyclic integral, which simply says that I am summing all possible heat interactions and work interactions that are happening over this cyclic process. And that's all that cyclic integral is supposed to mean. Other than that, nothing.
Thank you, sir.
Is that fine?
Yes, sir. Yes, sir. I got it.
Yeah, so I think, as a student, let me again point out that when I go through this set of lectures and when I come to this stage where, the first law has been introduced via the Carathéodory's statement, and as a result of that, the property called the energy for a system has been defined. It strikes me that nowhere, so far, the notions of heat interactions and temperatures have been used. And that's probably something sort of unique about this specific way of developing the subject. What we request is you please think about these matters carefully and see how you would like to incorporate these ideas in your class so as to minimize any confusions. Yeah, so let's try to move on to the Zeroth Law now. And, just like, the first law was considered, the Carathéodory's statement was considered to generalize behavior of adiabatic systems, where adiabatic systems were, by definition, only work interactions were permitted, Going to the Zeroth Law, it ends up generalizing the behavior of what we call a diathermic system. Okay, so just like adiabatic system, there's a terminology that we introduce here called a diathermic system, or you can even have it as diathermic partition or boundary. And the definition implies that a diathermic partition or a boundary will permit heat interaction between the system that we are looking at and its surrounding or the other system that it is interacting with. Okay, so that is the starting point for the Zeroth Law. Now, typically, I think our experience, and probably you will agree, is that if you open any standard textbook and look at the effort or look at how much space has been, allotted for Zeroth Law, it's actually very, very small. Okay, whereas the way the Zeroth Law has been formally expounded here by Professor Gaitonde, it's a fairly long drawn out process. We understand that. That is definitely appreciated. At the same time, we think that this really, sets the tone for understanding the idea of a property called temperature. And that's what really I wanted to mainly point out here. Okay, so maybe we can have some comment from Professor Bhandarkar and then have some discussion on this part.
No, I mean, I don't think I have much to add. It's just, you have already said it. It's we are trying to, again, it's a generalization of observations. And again, it's a statement which you can say is based on a culmination of all that we have observed. So, and we just introduce it to define, or let's say define or label something, something called as a temperature. That's all that we do. We must keep in mind that when we define the Zeroth Law, we do not really talk about high and low temperatures. We just talk about labeling a particular isotherm based on its heat interaction with other systems. And we just say that this is this isotherm, I can label it something like this. This is this isotherm, I can label it something like this. And then I just need to come up with a scheme to label those isotherms. That is all. That is really part of the Zeroth Law. I think that's about what we can add here.
Yeah, it appears, when you go through these videos that there is a lot involved, but that this is exactly the bottom line what we just heard from Professor Bhandarkar. And I'll just try to add one comment to this, is that perhaps you can appreciate that the notion of heat interaction has been then used to define the property called temperature. That's something that perhaps you can point out at the end of the entire discussion on Zeroth Law. Of course, we don't know whether students in your respective classes will really appreciate this level of detail, but I think it is useful. And a fairly similar discussion on the Zeroth Law, establishment of the isotherms, the corresponding isotherms, and then the labeling part of the Zeroth Law, as Professor Bhandarkar just mentioned, is something you will find in at least one textbook, which is a classic one, Heat and Thermodynamics by Zimanski and Detman. So that's one reference which perhaps you could note as far as the current Zeroth Law exposition is concerned. So that's also something that I wanted to point out. But it is very important to point out to the students that the Zeroth Law doesn't really tell us which is a higher temperature or lower temperature and so on. It simply establishes the idea of isothermal states, and the labels that we can then assign in principle to the isothermal states are what are called as, or is what is called as, the temperature level. That's all. No high, low, etc. It's just what is meant by assigning a property called the temperature. That's what is established by the Zeroth Law. I think that's all I have to say really. If there are any comments, you can try to post or discuss. Yes, so there is a comment in the chat box also. Maybe I will request Professor Gaitonde to look at it. Vednath Mathur, 1031. It's an interesting question actually. Yeah.
Professor Mathur, this is a very nice comment, and I have spent quite some time and discussed also with Professor Bhandarkar. In fact, one can go a step further and consider whether Zeroth Law is required if second law is there. The question is, I'm not sure whether it is required. Let me take an example from mechanics, because I get a feeling the situation is similar. The Newton's laws, the first law of Newton says that if there is no force on a particle, its momentum will not change. That means if it is stationary in our frame of reference, it will remain stationary. If it is moving at a certain velocity, that velocity will not change. Then the second law of Newton says that the rate of change of velocity is proportional to the force, or the force required to obtain a given rate of change of velocity is proportional to the required rate of change of velocity. That means this means there is a proportionality between rate of change of momentum and force. And if it's a simple proportionality, that means if force is 0, rate of change of momentum is 0. That becomes Zeroth Law of Newton. So one can argue that the Zeroth Law of Newton is included in the first law of Newton. In a similar way, one can argue that the Zeroth Law of thermodynamics is included in the second law of thermodynamics. But that argument requires that we explain second law without the use of the concept of temperature, because Zeroth Law is something which we use to extract the property called temperature from. And that becomes very difficult, particularly from the point of view of undergraduate engineering students, mechanical or otherwise. But remember that if you go through the Carathéodory's form of the second law of thermodynamics, which is not easy to understand because it is absolutely pure mathematics. Okay, then it is possible to go to first law, then second law, and the zeroth law comes out as one of those extended derivations from second law. Thank you.
Yeah, that's thanks for those comments, Professor Gatunde. So I think the issue here is perhaps that from a student point of view, it may not be that easy for that path to be followed. I think that's what we can conclude from that. And again, going back to how we have figured out that the students will understand things most correctly and without any confusion is through the sequence that we are following. Yeah, Professor Gatunde, go ahead.
Yeah, let me say that this is a very appropriate forum, because this is a course not really on thermodynamics. Directly, it is on the pedagogy of thermodynamics. And in pedagogy of thermodynamics, we have thermodynamics as the subject matter, we as teachers, and our consumers, that is the students. All three are involved in pedagogy. We can say that we and the students are the interactions, and the system is the knowledge base of thermodynamics. And hence our job is to see to it that the interactions are properly implemented. We want students to understand thermodynamics, and hence we should provide those interactions in a way that are digestible and understandable by students of thermodynamics, particularly students of thermodynamics in engineering, and in particular mechanical engineering. Thank you.
Yeah, thank you very much. Yes. Junaid, yeah, please go ahead. You had something.
Yes, sir. Actually, I just wanted to request Professor Gatunde, sir, just the way you have given some examples of system boundary at the initial level, at the beginning of first two lectures. So, in the similar way, can we also provide some examples of three bodies which are stated in the zeroth law? Then, accordingly, the students can understand what exactly are three bodies with some real examples. Because what I found over a period of time, students can understand the statements of the zeroth law, but it is difficult for them to actually realize and to actually imagine what are those three boundaries which can be a part of that zeroth law.
Okay, I think I'll note that, but what you say, not three boundaries. We have three systems,
Yes,
A
sorry,
and B and B and C.
yes.
And actually, I think there is an example there, but that's not very clear. That is an example in thermometry. In thermometry, we have the standard temperature system as one, the measuring the system whose temperature is to be measured, that is another, and the intermediate system, that is the thermometer, as the third one. Maybe I should write a real life example of this and include it somewhere. Thank you.
Thank you, sir.
Yeah, but basically, just taking off on what Professor Gatunde was saying, the notion of this thermometry, which essentially comes out of the discussion of the zeroth law, is what you could probably utilize to explain to the students, how these three bodies, which three bodies are we talking about, and so on. I think that's probably the most reasonable example that I can think of. Professor Bhandarkar, do you have any comment on this?
No, actually, I'm not sure what the question is really. What is the question?
Should I repeat, sir?
Yeah, please go ahead.
My question is that in a similar way, Professor Gatunde sir has given some examples of the boundaries, like it could be a real boundary, imaginary, moving, like that, with some slides, some real life examples of compressor, cylinder, and some lot of examples have been given, water bottle, something like that. In a similar way, can we add some more examples of something which can explain the zeroth law in a way that three bodies should be shown in that particular image?
Three bodies. Okay. Okay. I right now off the cuff, I don't know. So yeah, sorry. Maybe we'll come up with something. We can regroup and think about that. Thank you.
Achintya Kamli, you have raised hand. Please go ahead.
Sir, this is regarding the example. In our classes, what we talk about is if we want to measure the human body in terms of for any temperature measurement, we talk about the movement of the mercury column with respect to temperature. So what we say is that the human body is the body A, the glass which is conducting the heat is body B, and the mercury column which we are using to actually measure or infer the temperature is the body C.
May I say something? May I say
Yes,
something?
please go ahead.
I think this is incorrect. The glass of our mercury in glass thermometer is not one of the bodies. We do an experiment where the thermometer is in good thermal contact with me. That means the thermometer and I are at the same temperature. We form two systems which are in thermal equilibrium with each other. Now, after appreciating Zeroth Law, that means we come to a situation where my temperature and the temperature of the thermometer are the same. Then I note the state of the thermometer in which the location of the mercury thread is at some point X. Now, all I know is that now I know that my temperature and the temperature of the thermometer when the mercury thread is at a location X is the same. Now the question is, how do I label it? For this, I go to, say, a physics lab. And then in the physics lab, there are a number of different systems, each one at a different temperature. So all I do is I insert or bring my thermometer in contact with, say, one of them and find out whether when thermal equilibrium is reached, the stem of the thermometer is at that location X. If I can't find that situation with the first system, I go to the second system, third system, fourth system, and hunt out a system, let's say system K, where I said, when the thermometer is in thermal equilibrium with system K, its stem, the mercury thread is at the location X. And then I look at that system K, and system K says, I remain in a state where my temperature is defined to be 36.8 Celsius. Then I say, that means when my temperature was measured using that thermometer, was at a temperature of 36.8 Celsius. That's it. So here, for your illustration, the three systems are the system K, which is a standard system maintaining its temperature or its state such that its temperature is 36.8 K. Another system is me. The third system, which is intermediary system, is that mercury in glass thermometer.
Yeah, precisely. This is what I thought that you can use as an example, Junaid, to demonstrate the first law. So the mercury or liquid in glass thermometer is system A. It is brought in contact with say system B, which is a human body, and a thermal equilibrium is established, which is provided by that mercury thread rising to a certain level and remaining steady thereafter. And then you do the same thing with another body, which supposedly is at the same temperature as me, and realize that the mercury thread has again risen to the same level. And in that sense, you can establish that these three systems, so to say, be some other body and the mercury in glass thermometer as the third body are in thermal equilibrium with each other.
May I continue?
Yeah, of course.
Yeah, I forgot to tell you that although this is a long-winded experiment to measure my temperature, we simplify it. We don't take that intermediary called thermometer to a physics lab where all those different systems at different temperatures are located. Somebody has already done that, and somebody has already marked the different marks on the thermometer, not all the range, but the required range of maybe from 30 degrees C. to about maybe 35 to 45 C or 30 to 45 C. Okay? So that is known as calibration. And once it is calibrated, calibration means part of the experiment has already been done, and the result of that part of the experiment has already been marked on their intermediary called the thermometer by appropriate markings and graduation. So once that calibration is done, more than half the experiment or half of the experiment is done. So we can then do a temperature measurement with two systems. System A, the system whose temperature is to be measured, and system B, the thermometer, whose temperature has been quote unquote measured by calibration and the appropriate states at different temperatures marked by that graduation on the stem. But I think this is a very good example and I should write it down in longhand and include it somewhere. Thank you.
Sir, may I request one more example in such a way that the bodies are in not physical contact?
Yeah, we'll have to think about that. I saw your comment in the chat box. I think what we'll do is we'll think about that and probably get back to you guys a little later once we have come up with something that takes care of demonstrating the Zeroth Law correctly. So let me try to answer the last comment that has come in by Sanjay Gheji. Unfortunately, there is no such book right now in the same sequence that we are delivering. It's a good question actually, and in fact, a follow-up question could be, then why are we doing this in this fashion? And again, it's the same answer that we have been giving, that we think that this sequence really helps the students to understand, the material the most reasonable way without getting too confused. Yes, we absolutely agree that Szymanski begins with first chapter on temperature and Zeroth Law. That is absolutely correct. And in fact, if you go through that, you will realize that the explanation or the development of the first Zeroth Law is reasonably the same way that is being done in this set of lectures. So it's again Szymanski's way of looking at things. I mean, perhaps Szymanski thinks that that's the most reasonable sequence to follow. And I think he's within his rights to think that. And that's what we are trying to point out, to be honest with you, that we think that this is a very reasonable way of doing it, the way we are doing it here in these lectures, specifically Professor Gatonde. But you can think about it on your own, how you want to bring it. It's just that we keep on harping the same thing. Try to be consistent when you develop it whichever way, so that the students should not get confused and realize what is going on. Yeah, so it's a nice comment, the last one again in the and before that, the entropy part, we will of course take it up only when we discuss second law and the implications of second law. So we'll please hold on to that. Presently, let's try to wrap up this Zeroth Law discussion that we are going through. Yeah, in a way, you are right, Professor Mathur, that it's so obvious why need a statement or a law. See, the way at least I understand it is the way it has been done and the formality with which the Zeroth Law has been expounded is...
can I add here? I mean, I can only say that many things seem obvious only on hindsight, and of course you should realize laws are just, statements of how we observe the facts. But the fact is that till a long time people don't seem to be observing what is happening. It took all of Newton to figure out that there is something called gravity, whereas nowadays people may say, what is there? It's so obvious. So you should realize that there are definitely, this is all observation only. We are not stating anything different from observation. It's just how we have put it so that it cannot be disputed. That's all that is there.
Yeah, I think the formalization of the observations is what is the key here. That when you bring it in a very formal fashion, the observations get ossified in some sense, and that's what I think we are looking for.
Actually, sometimes the student feels that it's so obvious and we have unnecessarily made it more complicated by making a law and asking them to prove the law with the help of examples.
Yes, I understand the issue here, and certainly we also do face the same issues often. As I said, in terms of proving any of these, it's not possible because there is no proof. All that we keep saying is that these are generalizations of observations over so many years and centuries and so on. And that formal statement of that generalization is what we will call a law. And there exist different versions as well, as we have been pointing out. So we have utilized certain versions which we think are the most suitable for the development of the subject from a student's point of view. That's all that really is the bottom line here.
Yeah, that's true. Most of the book, while explaining Zeroth Law of thermodynamics, take this example that if they make two bodies and A and B are in equilibrium and B and C are in equilibrium, then A and C is in equilibrium. Now the student feels it's so obvious. What's
I agree, but the formality of establishing that statement is what really been done through the lectures here. That's
yes.
I hope you understand that.
Yes, sir. True, sir. Thank you very much.
Let me try to answer Mohammad Iqbal's 10:51 a.m. I think maybe Professor Bhandarkar can only answer that.
No, okay, yeah. I mean, I think the idea is we will try to write up something in this order and put it forth. I think that is what Professor Puranik was implying.
Yeah. So to be honest with you, yes, Mr. Mohammad Iqbal, the thought process is on that front, and an effort is being made. We hope that something we can bring out in the next 1 year or so.
Thank you, sir.
I hope it is going to be useful.
Yes, sir. Yes, sir. Thank you, sir.
See, Achintya, the videos are the entire set of videos is available on YouTube. So in that sense, they are open, publicly available and accessible. With Professor Gaitonde's permission, we can even provide you the list of the links to the YouTube videos. Is that? Yeah, Professor Gaitonde, is that okay?
Yes, that we can provide that, because rather than go through this whole course, that thing can be used, and all this course is in community commons, so open source. Correct. So long as, and it is CC BY 4.0, so that means so long as you use it fairly and give credit, you can do whatever you feel like with it. You can copy it a number of times, modify it, but only whenever you hand it out, you must provide the same type of conditions to the receiver, and provide BY means provide the reference to the original work. That's it. So maybe I'll again recreate that small directory, and we can upload it on this as a resource. Anybody who wants can download those links and keep.
Yes. So we have just a couple of minutes to wrap up this session, and one pedagogical point I wish to point out is the following. I myself have used a so-called flipped classroom to administer this course. And what we mean by flipped classroom is that I assign viewing of these certain number of these lectures per week to the students in the class. And the following week, roughly 3 hours, I only discuss issues and try to address questions based on the viewing, just the way we are doing it in some sense here. But of course, there is a lot more teaching involved when it comes to addressing students' questions. Here we are more or less discussing issues. And that's also something that you can think about once the lecture videos are available to you through the YouTube format or whatever that may be. One could think of using these lectures, in a flipped mode, where you ask the students to see some lectures and then in the following week discuss the matter, try to work out a few examples and so on to reinforce the ideas and the concepts and the learning. I think that's one sort of the tough comment that I wanted to provide now that the issue of these lectures came up and the videos on YouTube and so on. Yeah, you can certainly use flip. I do it myself here. So yeah, so last question on the chat box: can we apply laws of thermodynamics of course you can, pneumatic and hydraulic systems. These laws are universal in their applicability as far as the premises on which these are based are not violated. So there should not be any problem in application of these laws to any specific pneumatic or hydraulic system that you are dealing with. Oh, so Professor Gaitonde has provided the link on the... So I think we are at the end of this session now, and I hope the discussion has been useful again till this point. The succession has been reasonably clear as to how we are developing this subject. So now in the afternoon session from 2 p.m. to 4 p.m., we will start taking up the second law, and in particular lectures 20 to 23 are going to be taken up, and that's the introduction to second law, introduction of the notion of a heat engine, and discussion of temperature levels, and finally also we will have the reversible process finally discussed. So I think that's the set of lectures 20 to 23 which will be taken up in the afternoon session from 2 p.m. to 4 p.m. Is that fine? If that's the case, then we can break now and we will meet at 2 p.m. So that's fine. Thanks everyone. So see you in the afternoon at 2 p.m. Thank you.